Javier Gonzales Martín. Do you want to present him?
Sure.
Yeah.
Sorry. Today he's going to present a paper called the Latex-based Biofilms for Indoor Air Purification. He studied the degree of chemistry and holds a master's in advanced analytical techniques at Valladolid University. He's currently a PhD student at the Institute of Sustainable Processes, and his research focuses on the biotreatment of indoor pollutants.
Thank you for the presentation. So, welcome everyone. I would like you to present our investigation, latex-based biofilms for indoor air purification. So, recent studies confirm that indoor air pollution is a huge health problem. Every year, this problem is responsible for more than 4 million deaths worldwide, and also has remarkable economic consequences, such as the associated costs for the health system, and also decrease in the productivity of workers. And this problem is expected to go worse as the modern energy-efficient buildings tend to reduce ventilation, which is the simplest way to deal with this problematic. Every year, new pollutants and sources of pollution are being found in indoor areas. And traditionally, physical chemical technologies are being used for deal with this problem, but the particular characteristic of indoor air make these technologies far from being ideal to deal with this problematic. So, but biotechnologies emerge as a possible solution that can cope with the low concentrations, the variability, and the hydrophobicity of indoor pollutants, especially volatile organic compounds. Biotechnologies also has other drawbacks, such as the limited mass transfer, especially for hydrophobic compounds, and also the possible release of microorganisms to indoor air. So a possible solution is the application of polymer biofilms or biocoating, which is an innovative setup in which the microorganisms are embedded in a porous polymer matrix, isolated from each other in a non-growing state. So with this configuration, the natural formation of a biofilm would be prevented. So therefore, we would obtain a direct contact between the gas pollutant and the microorganism. So the mass transfer will increase. And additionally, this system would increase robustness, and also it would prevent the release of these microorganisms to purify indoor air. So in this context, we propose a series of experiments to investigate the influence on pollutant removal of these different formulations of biocoatings. So our setup consisted in 4 flat bioreactors or chambers of 1.4 liter filled with polyurethane foam as supporting material for the biocoatings. And an airstream, a polluted airstream, was simulated with these pollutants, NXN, trichloroethylene, toluene, and alpha-pinene, which were selected as model pollutants of representing groups of organic pollutants found in indoor air. So these pollutants were dispensed by a syringe pump in liquid state, and they were then vaporized by the gas flow to reach these concentrations. And the concentrations were measured by solid state microextraction and analyzed by gas chromatography with FID detector. So the different parameters of the experimental run are summarized in this table. In the first experimental run, the presence of latex in the mixture was investigated. Chamber 1 was used as a control, just adding a biomass suspension to the polyurethane foam packing. Chamber 2 was inoculated with a mixture of biomass pellet and latex, and chamber 4 was inoculated with a biomass suspension and latex. And chamber 3, only latex was applied as an abiotic control. So as we can see, the removals of hexane and trichloroethylene were low, but toluene and pinene removals were very high for the control and for chamber 4 mixture, biomass suspension and latex. On the contrary, the mixture of a biomass pellet and latex in chamber 2 only achieved moderate toluene and pinene removals, probably due to the lower water content. And in this experiment, unexpectedly, high removals were observed in chamber 3, probably due to contamination. In the second experimental run, the presence of hydrogel as a water retainer was investigated. Again, chamber 1 was used as a control, and chamber 2 was inoculated with a biomass pellet and latex. In chamber 4, the mixture was similar, but adding 50 hydrogel beads, which were previously hydrated with mineral medium. And chamber 3 was again left as an abiotic control, but just with packing material. So as before, hexane and trichloroethylene removals were very low. Only the control in chamber 1 achieved high hexane removal, but after a 100-hour acclimation period. Toluene and pinene removals were very high for the control. On the contrary, chamber 2 with biomass pellet and latex did not achieve good removals. But in chamber 4, with the addition of hydrogel beads, a moderate toluene removal was observed, but not as high as in the control. Pinene removal was very high in chamber 4, but again, an acclimation period was observed. In experimental run 3, the water content of the mixtures was investigated, and as before, chamber 1 was used as a control, and chamber 2 was inoculated with a biomass pellet and latex. Chamber 3 was inoculated with a mixture of biomass suspension and latex, and in chamber 4, a biomass pellet was mixed with a pre-dried latex. So hexane and trichloroethylene removals were similar to the previous experimental run. Only chamber 1 achieved moderate hexane removal. And toluene and pinene removals followed the different water contents of each mixture. So first, the control achieved very high removals from the beginning, followed by the mixture in chamber 3 of biomass suspension and latex. The mixture in chamber 2 of biomass pellet and latex only achieved moderate pinene removals and only for a short period of time. And finally, chamber 4 did not achieve any good removals. In experimental run 4, different mineral medium contents were compared. So now in chamber 1, only a biomass pellet was used as a control. Chamber 2 was inoculated with a biomass suspension and latex, which was previously treated with active carbon. In chamber 3, only 20 milliliters of biomass suspension were used for the mixture, and in chamber 4, 40 milliliters of biomass suspension were used for the mixture with latex. As before, hexane and trichloroethylene removals were low during the whole experiment, and toluene and pinene removals increased with the increase in the mineral medium content of the mixture. Now the control only achieved high removals at the beginning, and this could be explained by a progressive loss of moisture in the biofilm. And pinene removals were very high for all the biocoatings, but again, an acclimation period was observed. And finally, in experimental run 5, different biomass contents were compared, and then in a second stage, the pollutant loading rate was increased. First, in first chamber, a biomass suspension was used again as a control. In the second chamber, a mixture of biomass suspension and latex was used, and this mixture contained 0.5 grams of biomass. And in chamber 4, the mixture was similar, but with 2 grams of biomass. And chamber 3 was again left as an abiotic control with latex in polyurethane foam. So in the first stage, this abiotic control achieved moderate toluene and pinene removals, which could be explained by absorption of the pollutants. And all the chambers with biomass achieved very high toluene and pinene removals at the beginning, but the removals of hexane and trichloroethylene were low. In the second stage, again, hexane and trichloroethylene removals maintained the low removals. And chamber 1, after the pollutant loading increase, just lost all the good removals. This fact could be attributed to a rapid loss of the moisture and therefore the death of the biofilm metabolic activity. On the contrary, chamber 2 and chamber 4 with biocoatings were able to keep the good removal rates until the end of the experiment. And between chamber 2 and chamber 4, no big difference were observed due to the different biomass contents. So as a conclusion, we have generally seen very high toluene and pinene removals, but on the contrary, we did not observe good hexane and trichloroethylene removals. So this could be explained either by mass transfer problems or by metabolic limitations of our biomass. The essential role of water and nutrients was demonstrated in several experimental runs. Our biocoating achieved removals as high as in the controls with biomass in suspension, which was previously reported. And also, our biocoating achieved very high robustness when the pollutant loading rate was increased, which could be a good opportunity for high treatment capacities. And finally, this is the first real-scale study with biocoatings for the simultaneous treatment of several volatile organic compounds, and also with a mixed consortium of microorganisms. So thank you for your attention. And if you have any questions.
Thank you very much, Javier. We have a couple of minutes for some questions from the audience. No questions. Okay. So, Javier, how do you see the applicability of these latex biocoatings for real earth treatment?
Well, at the moment, we are working just for indoor spaces, which is a limited amount of gas. We are not working for big industries or big water treatment plants like other technologies that have been presented. But I think it's a good opportunity for develop these new packing materials or these new configurations that would allow us to increase the mass transfer, which is a big problem for some organic pollutants.
Yeah. Thank you very much. So if there is no question, we move to the next speaker.